Let's take a look at a trig function and see where its critical points are. Now for trig functions, we know a lot of times they repeat themselves. So we're going to have an interval for this. We want to figure out the critical points on the interval negative 2 pi to 2 pi. Notice they have brackets, so we will include those on a closed interval. Now here's our function. It's a little weird. It's 2 cosine of theta plus sine squared of theta. And so just remember that when you are, first of all, let's remember to put parentheses around theta where necessary, right? Remember that whenever you're finding critical values or points, the first thing is to take the derivative, and we can do that. These are just some trig functions. Might have to do a little bit of a chain rule here. So the derivative of 2 cosine is negative 2 sine. The derivative of sine squared, pull the 2 down, so it's 2 times sine of theta, times the derivative of the inside, which is sine, so cosine theta, so it's 2 sine theta cosine theta. Now remember, critical values exist where the derivative equals 0 or it doesn't exist. Now we can see this is going to exist everywhere. Sine of theta has, you can plug anything into it. The domain is all real numbers, same for cosine. So we don't have to worry about where this equals 0. Now the question is how you solve for this. Well, fortunately, they have a GCF of sine. Pull the sign out, right? Be left with 2 factors. Now, they also have a 2 in common, and since the first term is negative, why not pull out a negative 2? So just pull out a negative 2 sine of theta from both of these, and it's going to be left with 1 minus cosine theta. Okay, and the negative times negative is a positive, and that's why. Then you're going to set each factor equal to 0, so set negative 2 sine of theta equal to 0, and divide by negative 2 to get sine by itself, so you're going to have sine of theta equals 0. Now we go to inverse sine, or what I like to call arc sine, to get theta by itself. The real question is, where on the unit circle does sine equals 0? Where does the y value equal 0? And for our particular domain of negative 2 pi to 2 pi, it'd basically be every multiple of pi, okay, because that's on the x-axis, where the y value equals 0. So negative 2 pi, negative pi, 0 pi, and 2 pi. Tons and tons of critical values right here, okay? That's why we had a limited domain for this one. Now remember, we have to set the other factor equal to 0, so 1 minus cosine of theta equals 0. Now fortunately for this one, we add cosine of theta, we take the inverse cosine. What's inverse cosine of 1? What does cosine equal 1? Well, it's only on multiples of 360. Remember, it's not at 180 because it'd be negative 1 on the unit circle, so negative 2 pi, 0, and 2 pi. So fortunately, we just got some overlapping critical values. We don't have to do them twice. It's the same critical value. So basically, we'll just be focusing on these 5. And again, like we talked about, this exists everywhere. So for step 4, no need to figure out where it doesn't exist. It exists everywhere. Step 5, we're still going to write out all of our critical values, and remember you need points, so we're going to plug them back into the original. We're going to plug each of those back into the original. Cosine of negative 2 pi would be 1. It's the same as 360. It's the same as 0. And then sine of negative 2 pi would be 0. So first critical point, we plug in negative 2 pi, we get 2 back. Okay. The next critical value was negative pi. Cosine of negative pi is negative 1. We're going to get 0 over here all the time, right? So that's negative 2. So the second critical point is negative pi, negative 2, because I plugged in negative pi. Third critical point, plug in 0. I get 1 back for cosine and 0 again for sine. So it goes 0, 2. So it looks like the y value is either going to be 2 or negative 2. Let's take a look. Yes, when I plug in pi, I go back to cosine of pi, which is negative 1. So my next critical point is pi comma negative 2. Again, this is always going to turn to 0. Lots of critical points. And finally, plug in 2 pi, I get 1 again. Final critical point is 2 pi comma 2. So here's what it looks like. The strange looking cosine function, it really levels off at the top. But we can see why these are critical points, okay? They have horizontal tangents, and as a result, there's a possibility that they change direction. In this case, for every critical point, it indeed changes direction. So that's it for this trig example of critical points. If you have any other questions about it, let me know.